Okay, so it's 3:30. I know people are still coming into the meeting, so we'll start off a little slowly because we're going to have the first 30 minutes of class in breakout rooms to discuss the Geo-Connection videos. So we'll make sure that I wait a couple minutes so that most people are here before I put you into the breakout rooms. Before we get started with that, does anyone have any questions from last class or from last week about igneous rocks and volcanoes? Or any questions about the exercise that's due this Sunday? Okay, so as I said, we'll start class with the Geo-Connections discussions. And so we'll have 30 minutes for that. And so you'll be in breakout rooms with the group of people that's on the list that's on Blackboard that says for the Geo-Connections discussion groups, and that you should have watched their videos and have thought about some questions you have about individual presentations or just things that you think would be interesting to discuss with the group, either related to your presentation or one of the other presentations that you watched. So we have in those 30 minutes, the first 25 minutes will be to discuss the presentations themselves. And then we'll have 5 minutes where you can kind of reflect on the assignment overall and give me some feedback. And so I have a Google Doc that I'll paste that link into the chat where you can record some of your feedback. So within those first 25 minutes, most groups have 5 or 6 people in the group, and maybe one of those people might not have submitted their presentation yet. So you have maybe 5 presentations to discuss, maybe 6 in some other groups. So it should be about 5 minutes for each presentation. So just keep a little bit track of the time. I'll send a little broadcast, a message to the breakout rooms, every 5 minutes to say, oh, you might want to move on to the next presentation, just to help you keep track of time. If people aren't here, you might only have 4 people, and then you can spend a little bit more time. So but about 5 minutes for each one. While you're discussing your presentations, I'm going to drop into some of the breakout rooms just for a couple minutes at a time. Just to listen, because I think it's really interesting. Last class, I heard a lot of interesting questions being asked and good discussion happening. So I like to hear that discussion the same way that I really enjoy watching your presentations and learning about usually topics that maybe I hadn't considered that have interesting connections to geology. Okay, let me copy this link. Okay. So that's the link in the chat. There is the Google slide where you'll record your kind of reflections and feedback on the Geo-Connections assignment. So there's one slide for each group. So once you're in your breakout rooms, you'll be able to see which breakout room number you're in. You'll just record it on the slide for your breakout room. And so the first question I asked you to think about how effective the assignment was in helping achieve overall course learning objectives. And those are listed in the notes section of the slide. So if you want to refer to that there, it's down there. Okay, any questions before I open up the breakout rooms? If you do have any questions that come up while you're in the breakout rooms, feel free to use that ask for help button to call me into your room. And as I said, I'll drop into some of the rooms while you're talking. I won't drop into the rooms in the last 5 minutes when you're doing the kind of more reflection and feedback part. But yeah, don't feel nervous when I come into your room during the just while you're discussing. Okay, so I'll go ahead and I'll open up those breakout rooms. And then I'll see you all back here in the main room in 30 minutes from now. Okay, so it looks like we're all back from the breakout rooms. Let me restart my screen sharing. So hopefully you all enjoyed the opportunity to view each other's presentations. As I mentioned earlier, I always really enjoy seeing what people came up with and learning something new myself. So at the end, you were thinking a little bit about how this assignment related to some of the learning outcomes at the course level, right? So thinking about the process of science and how we can bring together geoscience and other fields of knowledge to address interdisciplinary problems, and then also think about how we, learn and communicate about Earth science. So we're going to shift gears a little bit now and turn our attention more to the second overall course learning objective and think about making observations and interpretations of the geologic record. Right. So let's think about some examples of how geologists have interpreted the geologic record. So how have geoscientists deduced that 5.5 million years ago, the Mediterranean Sea almost completely dried up? Or how have they deduced that water once flowed on the surface of Mars? Or that a few hundreds of millions of years ago, the entire Earth was almost completely covered in ice during this event known as the snowball Earth? Well, the answer to all of these is sedimentary, my dear Watson. These are really interesting events in Earth's history that we have learned about from the sedimentary record. Right? And so our topic for today and for next class is looking at sedimentary rocks and understanding the processes that go into creating these sedimentary rocks so that we can then know what to look for in these rocks in order to make interpretations about what the surface of the Earth was like in the past, right? So we also talked about these different types of rocks in terms of thinking about Earth as a system and how material moves through the Earth system in the rock cycle. So that's this diagram that we've seen before. And so again, today we're focusing on sedimentary rocks, right? And so as I said, sedimentary rocks, right, are rocks that form initially from weathering of some other rock at the surface that breaks down that older rock. That material then gets eroded and transported away, eventually deposited as sediment, and then lithified to form sedimentary rocks, right? And so we're really interested in understanding these processes so we know how to interpret the rock record. And we need to know what we need to observe within these rocks. So in the case of igneous rocks, for example, we looked at the grain size, the texture of those igneous rocks, and that told us something about the rate at which those rocks cooled and where they cooled, whether it was at the surface or deep underground. If we look at sedimentary rocks, we might also be interested in the grain size of that sedimentary rock, but that's going to be giving us different information. It might be giving us information about how energetic the environment was, whether there was fast-moving water or slow-moving water, where that rock deposited. And more generally, sedimentary rocks are telling us about what was happening at the surface of the Earth at the time that these sediments were deposited. So let's take a 5-minute break before we get more into more details about sediments and sedimentary rocks. And during that 5-minute break, I'll be playing this video that actually talks about one of those events I mentioned just a minute ago of when the Mediterranean Sea completely dried up 5.5 million years ago.
Geological mystery. Since the 1800s, scientists have known that the layers under the floor of the Mediterranean Sea weren't just made up of the usual sediments like mud and sand. Instead, they're full of salt crystals, lots and lots of salt, forming mega deposits so large that they're sometimes called the Mediterranean salt giant. And salt deposits like these are typically found in places where bodies of water have dried up. So the existence of this salt giant suggests that at one point in history, the Mediterranean Sea must have evaporated. But how could a body of water as big as the Mediterranean Sea just disappear? It would take decades and more than 1,000 research studies to even start to figure out the cause or causes of one of the greatest vanishing acts in Earth's history. Today, ocean water flows into the Mediterranean Sea from the Atlantic through a narrow passage between Europe and Africa called the Strait of Gibraltar. And that's the main source of water for the sea. Some freshwater in the form of rainfall and rivers also flows into it, but that's not enough to keep the sea filled up without the water from the Atlantic, because it has very high rates of evaporation. So, to the geologists who were trying to explain the existence of the salt giant, it looked like the main water source to the Mediterranean had somehow been turned off, like turning off a faucet in a bathtub. They called this event the Messinian Salinity Crisis, or MSC. But it wasn't easy to figure out how that water source got turned off, and researchers have been arguing about it since the 1970s. How did it happen? How long did it take? In the end, they came up with 3 main hypotheses to answer these questions and to explain how the salt giant got there. First, some scientists thought there was a global cooling event at the beginning of the crisis in the late Miocene epoch around 6 million years ago. If the whole world cooled off into an ice age, then lots of water would have been taken out of the ocean and frozen in glaciers, reducing the water flow into the Mediterranean Sea from both the Atlantic and the rivers. An event of this magnitude would have had to have been global, not local. However, this idea was proved wrong pretty quickly. Soon after the salt giant was discovered, researchers started studying oxygen isotopes and other geochemical data from sediment and ice cores around the world. Their data showed that the rest of the Earth wasn't abnormally hot, cold, or dry during the crisis. Plus, they found that some of the salt was deposited before any changes in sea level. So there doesn't seem to be a cooling event that was big enough to turn off the flow of water. That ruled out the first hypothesis. The second idea was that tectonic events had somehow blocked the Mediterranean off from the Atlantic and cut off the water flow. Some researchers thought that shifting ocean crust slowly blocked off the waterway between the Atlantic and the Mediterranean. As the water left behind in the deep basin evaporated, it became saltier and saltier, depositing layers of salt as it dried. And this explanation was almost right. Other scientists thought that it might have been a combination of shifting crust and climate change that made the Mediterranean dry up. This was the third hypothesis. According to this model, the crust under the Strait of Gibraltar rose up over time, reducing the flow of water from the Atlantic. Then, because of changes in regional climate, like periods of less rain and higher temperatures, the amount of fresh water that made it into the Mediterranean varied. So by this thinking, the MSC didn't happen all at once. Instead, water levels started to drop after the strait closed and then fluctuated according to changes in the climate. And this hypothesis ended up being pretty much right, or at least close to it. As geologists began collecting evidence to test these hypotheses, they eventually found that the MSC was indeed caused by changes in Earth's crust, but those shifts actually happened repeatedly, not just in one fell swoop. For example, in sediments near the Nile, geologists found evidence of repeated erosional events, not just a single big erosion. This means that the water level dropped, created a new shoreline for a bit, and then dropped again a few more times. Some researchers estimate that there were 16 climate cycles just in the beginning of the MSC. And these changes also correlated pretty closely with what we know about climate cycles. During periods of decreasing sea level, the position and angle of the Earth changed with respect to the Sun, so there were periods of lower solar energy and others of higher solar energy, which increased evaporation rates in the Mediterranean. At the same time, an actively folding and uplifting tectonic belt caused water input to decrease. Researchers were able to use chemical and even magnetic signatures in sediments laid down during this time to estimate how long the MSC lasted. And the data suggests that it went on for over 600,000 years, with the very driest period occurring about 5.6 million years ago. At the height of the MSC, external water sources were completely cut off, and most of the water left behind in the Mediterranean basin was evaporating. Geologists think that the water level dropped by a few hundred meters, the length of multiple American football fields. And the water that was left was super saturated, so the salt continued to precipitate out at the bottom of the sea. The longer there was salty water that could precipitate out salt, the thicker the final deposit became. And the salt giant is possibly up to 3 kilometers thick, which means that the sea was extremely salty for the hundreds of thousands of years during the MSC. And this, of course, had enormous effects on living things in and around the Mediterranean. Back then, life in the sea was dramatically different. Today, the Mediterranean Sea is home to thousands of marine species and is famous for its crystal blue water. But when the sea almost dried up completely, it became uninhabitable. Almost nothing could live there. Most of the animals and plants that lived in the Mediterranean before the MSC either migrated away or died because the water was too salty and too shallow. Some marine
Okay, so we can come back from the break. Okay, so we'll, as I said, we're focused on sediments and sedimentary rocks. So I'll start by just kind of defining what we mean by sediment or sedimentary rocks, right? So this is all material that is deposited at Earth's surface, right? And sediment is loose material, so fragments of rocks or minerals or shells. Yeah, it can also be material that's been precipitated out of water. So if you're watching the video during the break, it was talking about these big salt deposits, right? These are also a kind of sediment, right? That's deposited at the surface of the Earth. So sediment would be things like sand and mud and gravel. Then when the sediment gets compacted and it gets cemented together into a solid rock, then we would consider that a sedimentary rock, right? And so what these have in common is that they're deposited in layers at the surface of the Earth. So in this photograph here, we can see layers of rock. In some cases, they stand out because they're slightly different colors between the layers, or some layers are a little more resistant to erosion and stick out a little bit farther. But the sediment is deposited in these relatively small layers that we call beds. So we can describe this layering as bedding when we're talking about sedimentary rock. So here's an example of kind of one bed within this sequence of sedimentary rocks. And as they're deposited in layers at the surface of the Earth, we have older layers that are deposited, and then younger layers get deposited on top of that, right? So looking at these rocks, we know that we're going from older rocks at the bottom to younger rocks at the top. So the fact that these rocks are deposited in layers like this make them a really valuable record of past environments, because we can look at and see change over time by looking at these successive layers, right? So we can look at any one layer and kind of get a snapshot of, at that time, what was the climate like? What was the depositional environment? So was this at the bottom of a lake? Was there a river here? Other environments. Yeah, and we can also kind of infer things about the geography, because we can even look at some of the structures within these sedimentary rocks and figure out what direction water was flowing and how these different environments relate to each other. So the slide that I have up here is just an example of some of the work that I've done. So my PhD actually relied on looking at sediments and sedimentary rocks that were 1 to 5 million years old to infer something about the growth of this mountain range in the eastern part of the Andes in Argentina. So if we look at this environment today, we can see that on the east side of the mountain range, it's very wet, and we have these big rivers that flow from west to east away from the mountain range that have, they carry a lot of large boulders and things like that. And we have this lush vegetation from the wet climate. Whereas on the west side of this mountain range, it's a lot drier, right? And there's smaller rivers that flow down the length of the valley. And the sediment carried by those rivers looks a little bit different too. And so what I did was I looked at some of these older rocks within this valley that are maybe 5 million years old, and to see how the environment recorded by these rocks reflect changes from an environment that might have been more like what we see to the east today to the present environment. Okay, so anyway, as you might guess, I can get pretty excited about sedimentary rocks, and I have to always resist the urge to just tell you everything that I know and love about sedimentary rocks. But I want to make sure that we don't, get too overwhelmed, and so I want to actually start by thinking the more relaxing way about sedimentary rocks by thinking about modern depositional environments, and just imagine yourself relaxing in one of these different depositional environments. So when I say depositional environment, this means a type of environment where sediment gets deposited. So I have a few examples of a mountain stream, a desert, a meandering river, a beach, a lake, and a tropical sea, in this case showing like a coral reef. And so I want you to pick one of these to think about, and you can just imagine yourself doing this relaxing activity in this environment and thinking about the sediment that you would expect to find in that environment, right? So you can think about what would be the composition of that sediment, the grain sizes. So if you imagine picking up a handful of that sediment and looking at it closely, what grain size would you have? What would the shapes of the grains be? Are there other kind of features you might notice? Would you have sediment being deposited in flat layers? Or would you have things like dunes? And then also think about how the sediment's being moved around in this environment, right? And so I want everyone to take just a minute or two to think about this, and I have a poll question where you can record just what you came up with, right? So include both the environment that you chose and some brief description of either the type of sediment you would expect to find there, and or the processes that you would expect to see there, right? So this poll is open. I'll go back to the other slide so you can look at the pictures for inspiration as you think about this. And then the reason to do this is kind of two reasons that I wanted to introduce it this way. Is one, to recognize that we can use what we know already and what we see in the environment to help us understand these geologic processes. And two, because it is this understanding of these processes that then we can apply to look back and make interpretations of rocks, right? Okay, so I will be quiet for a couple minutes and just give you a chance to think and answer the poll question. Right, so some of the things that people have noticed are, the size of the sediment, right? In the mountain stream, you have relatively coarse sediment, and that size of that sediment varies even within that stream based on the speed that the water's moving, right? Whereas in a slower moving river like the Mississippi, you have much finer grained sediment, right? Some people thought about the source of that sediment. So in the mountains, the type of rocks that you see in that sediment might be reflecting what types of rocks are in the mountains nearby. Yeah. So basically, you can look through these yourself later if you want. But basically, we're thinking about variations in the type of sediment, right, based on what processes are acting in that environment, right? And so that's one thing that people that study the sedimentary record really think about is how is what we observe in that geologic record, in the sediment, in the sedimentary rocks, tied to the processes, and then which processes are kind of most important in these different environments that we might consider. Okay. And so we can think about this to understand the wide variety of depositional environments we see on Earth. We can even apply this to other planets. So our scientist spotlight for this week is Frances Rivera Hernandez. She's a professor at Georgia Tech who studies planetary geology and also sedimentology. And so she actually looks at rocks on Mars using imagery and some of the instruments on the Mars rovers to make interpretations about past depositional environments on Mars. And she also studies especially kind of extreme environments on Earth that could serve as analogs for some of these ancient Martian environments. Okay. So when we think about sediment, right? So far I've asked you to just imagine what kinds of sediment generally you might find in a location based on your own experience, right? We haven't talked about kind of the language that we use to describe these sediments within geology. So when we're thinking about sediment, there's a few kind of broad categories of sediment that we can think about based on kind of where this sediment comes from. And the first one are clastic sedimentary rocks, or clastic sediments. And these are formed of fragments of rock debris, little pieces of rocks and minerals that have been broken down through weathering and removed by erosion and deposited somewhere else, right? The second type are chemical sedimentary rocks, and these are formed by precipitation of minerals out of a fluid, out of water. And so that could be in a lake that dries up and becomes very saturated in those particular ions that makes up that mineral, and then it precipitates out those ions. So this picture here shows salt, right? That has been deposited in this dried up lake bed here. And then a third type of sediment we can think about are biogenic sediments. And so these are actually composed of plant and animal remains. And so that might include something like what's shown here is coquina, which is basically crushed up shells that then have been deposited and get cemented together to make a rock. Or another example would be coal, right, which is made up of plant remains. So coal would be an example of an organic biogenic sedimentary rock, whereas limestone is a sedimentary rock made up of calcite, where that calcite is usually derived from the parts of organisms that draw that calcite out of the water and use that calcite to build their shells or their skeletons, right? So that's an example of a biochemical sedimentary rock where you're precipitating out a mineral, which is calcite, but it's being done mediated through a biologic process, right? Okay. So in this course, we're mostly going to be focusing on clastic sedimentary rocks. They're kind of the most abundant type of sedimentary rock. We'll also look a bit at limestone because that's another very common sedimentary rock. And we'll just talk briefly about some examples of chemical sedimentary rocks. So I'll start by talking about about limestone, which is an example of a biochemical sedimentary rock. And then we'll talk very briefly about chemical sedimentary rocks, an example, which is evaporites. And then next class, we're really going to focus on the clastic sedimentary rocks. We'll start to introduce them at the end of class today, but then we're going to go into a lot more detail on those clastic sedimentary rocks next class. Okay, so looking at our learning objectives, right? As I said, I'm gonna start by talking about limestone. So that's one of the rocks that you will want to know how to identify. And I'll talk a little bit about the depositional environment in which limestone forms. Okay. So limestone is basically any sedimentary rock composed of the mineral calcite, right? And for most limestone, this calcite is derived from the shells or skeletons of organisms. And so that's what makes it a biochemical sedimentary rock, right? So there's basically calcite, or the ions that make up calcite, right? So calcium and carbonate ions dissolved in water. The organisms kind of pull those ions out of the water to build their shells, their skeletons. When those organisms die, that sinks to the bottom of the ocean and becomes that sediment, right? And there's lots of different kinds of limestone. I'm not going to test you on the different kinds of limestone, but when you're asked to identify limestone, there's many different varieties of limestone that you might that you need to be able to recognize as limestone, not worrying about what their specific names are. So here's some examples. On the left is coquina, which is basically crushed up shells. The middle picture is a fossil limestone, which is just a limestone that has lots of fossils in it. In this case, in the picture, there are coral, right? There's pieces of coral. There's some little fragments of shells in here. And there's these round pieces are pieces of crinoid stem. That's an extinct animal that lived in the ocean. Here's a more intact crinoid stem. And you can have fossil limestone that isn't quite as packed with fossils as this example. So I have, here's a sample of fossil limestone I picked up in Argentina that you can see it has just a few of the kind of orange colored things are shell called turritella. Okay. And then you can also have limestone that is pretty nondescript, just fine grained limestone where you can't see really much of any features in it. But if you look at it microscopically, it's made up of either tiny organisms or tiny fragments of calcite that was once part of some organism. And so this fine-grained limestone is called micrite. As it's referred to as micritic limestone. So it's like micro, right? So it's just very fine-grained. And so this would have been initially some carbonate mud, right? So like normal mud, except that the composition is calcite rather than clay minerals. And then it lithifies into this micrite limestone. And here's another example at the bottom, chalk. This is a picture of the white cliffs of Dover. And so chalk is actually made up of the tiny skeletons of these microorganisms called coccolithophores. So these are planktonic organisms that are floating around in the ocean. And when they die, they settle to the bottom of the ocean and it creates this rock that we call chalk. There are a few kinds of limestone that the calcite is actually precipitated directly from the seawater and is not made up of parts of some organism. And one of these is what we call oolitic limestone or oolite. And it's made up of these little spherical grains of calcite called ooids. And so these form in these really high energy environments where there's warm water that's supersaturated with calcium carbonate, so that calcium carbonate can precipitate directly out of the water. And as the waves kind of move around these grains, the calcite continues to precipitate in layers around these grains that makes these little round grains that then can get cemented together into this oolitic limestone, right? So you can see the little circles making it up. Another kind of interesting type of limestone you can find stromatolitic limestone, so limestone that has what are known as stromatolites. And these are these kind of mounds with layered mounds within the rock that are actually microbial mats, so cyanobacteria that grows in these layers, and the kind of sticky layers of cyanobacteria traps calcium carbonate that's being precipitated out of the water and helps build up these mounds or these columns to create these stromatolites. So this is a picture of modern stromatolites in Shark Bay in Australia. And these are really uncommon today. They only form in these extreme environments where you have kind of like hypersaline water, but they're more common in the ancient rock record. So I have on my desk another a sample of a stromatolite where you can see that there's these kind of mounded layers within this carbonate rock. So for all these different types of limestone, right, the one thing they have in common is that they're made up of calcite primarily, right? So if you wanted to identify a rock as being limestone, you would want to be able to recognize it's made up of calcite. So the easiest way to do that is to put a little drop of acid on it. And if it fizzes and bubbles, then you know that this rock is made up of calcite, right? Some other things you could, if you're looking around, you're like, well, maybe it's calcite, maybe it's quartz, you could try scratching it. If it scratches easily, it's more likely to be calcite than quartz. Another thing that all of these different types of limestone have in common is that they're deposited for the most part in warm, shallow marine environments. So marine means sea, right? So warm, shallow seas. So when you see limestone rock and you're trying to make some interpretation about its depositional environment, you're going to think warm, shallow sea, right? And then, at a kind of more advanced level, you could look at some of the other characteristics of that, and it could tell you more detail about, what processes are happening within that environment. But for this class, I'm not really going to test you on that. But this is just showing an example of in a higher energy environment where you have waves breaking, you might have some coarser limestone, like this fossil limestone with big broken pieces of coral. And in a more quiet environment where there aren't a lot of waves and the water is very still, this more fine-grained sediment is able to settle out and be deposited on the seafloor, and you might be more likely to have micrite, right? Okay, any questions about limestone? Yeah, Jacob.
So I was just wondering about like these limestone caves that form, like especially like Luray Caverns in Virginia and that area. So is that basically because over time that part of Virginia was like underwater and maybe in these types of marine environments, and then it was like it just there's like the plates moved and then it gained elevation, and then so like. Is that just like these caves are just full of like these marine stuff?
Yeah, that's right. So Virginia, maybe about 450 million years ago. There's been various times throughout Earth's history that the environment has been shallow marine in Virginia, but during the Paleozoic, for some of the time it was just a stable, shallow marine environment, and there was a lot of limestone that was deposited. And then later, we have things like the collision of Africa with North America that created these mountains and created Pangea. And so we have these big changes that happen over time, and many other layers of rock have been deposited on top of that. But generally, yes. So when you see these thick deposits of limestone, in Virginia or elsewhere, it's saying that at that time it was a shallow marine environment. And then, today, now it's being weathered through dissolution, and you actually get then limestone being precipitated, calcite being reprecipitated within these caves, forming things like stalagmites and stalactites. But the original limestone itself would have formed in these types of marine environments. Okay. So then looking at chemical sedimentary rocks, as I said before, these are sediments that precipitate directly out of water. So you have ions that are dissolved in the water. Those ions come together and precipitate out, grow little crystals of these minerals. And so one way that we can have minerals being precipitated out of the water is if you evaporate the water, right? As you start evaporating the water, the concentration of those ions increases, right, to the point where it becomes saturated or supersaturated, and then those minerals can precipitate out of solution And of course, if we completely dry up all of the water, then everything that was dissolved in the water ends up, precipitating out. So these sediments that form through this process of evaporation are called evaporites, right? And so they're going to form in environments where you have very high rates of evaporation, right? So dry climates, so the arid marine shoreline, that means dry climates along, like the seashore. Desert lakes, also known as playas. So this picture on the left is an example of a playa. And restricted basins means basically like if you have a bay that's maybe connected to the ocean and then it gets cut off, you have this salty water that then starts evaporating more because you don't have it, it's not being replenished by a connection to another input of water. And that can cause really, really thick deposits of evaporites, like we saw in that example of the Mediterranean Sea getting cut off from the Atlantic and drying up. So some of common minerals that you'll find in these evaporites include halite, which is salt, right, NaCl, and gypsum, right, which is that calcium sulfate mineral. So this picture on the left is showing deposits of halite in a dried up desert lake. And the picture on the left shows some thicker evaporite deposits where the main mineral in this rock is gypsum, making up these white layers in the rock. Okay. So these aren't rocks that I would test you on directly, but you might be asked to interpret a depositional environment of something like a desert playa, and knowing that evaporites form in this environment would be helpful to interpreting that environment of deposition. Okay. Okay, so and as I said, these evaporite deposits that allowed geologists to determine that the Mediterranean Sea almost completely dried up 5.5 to 6 million years ago. Okay. Okay, so I think we just have a few minutes in class, so I don't think it's necessarily worth starting talking about clastic sediments. But we'll start here next class and talk about the different processes that go into creating a clastic sedimentary rock, beginning with weathering, followed by erosion, transport, and deposition. And we'll spend quite a bit of time thinking about how that sediment changes as it's being transported and deposited, and then how we can interpret that in terms of the depositional environment. Okay, so are there any other questions before we go? Yeah, Cora.
Okay, so I'm just wondering, so limestone and evaporites are both two like classifications of different types of sediments. Like, are they like the two like different types of sediments, or like what's the, yeah, I don't know. Does that make sense?
Yeah, so there are two types of sedimentary rocks. So if we're thinking more broadly about classifying sedimentary rocks, we can say clastic, chemical, and biogenic. So evaporites would be an example of a chemical sedimentary rock, and limestone, most limestones are an example of a biochemical or biogenic sedimentary rock. And so then the limestone is the name we give specifically to that rock that's made up of calcite. Evaporite is a little bit more general term for chemical sedimentary rock that's formed as a result of evaporation. Does that answer your question?
Yeah, I just wanted to understand to make sure that they're both like generalized terms. Yes. Okay. Yeah, that made sense. Thank you.
Yeah, those are terms you would use to, like, you find a rock and you're like, what am I going to call this rock? You can call it limestone, or you can call it an evaporite. Yeah. Okay, well, then that's it for today. As I'm sure you all know, you have a couple spring break days coming up next week, including on Tuesday. So I will see you all again next Thursday, and enjoy your weekend and your spring break days.